Ok, dovremmo essere partiti. All right. Okay, so good afternoon, everybody, or good morning if you are in a morning time zone, or good evening if you're in an evening time zone. So this is the latest of Machine Learning for Science seminar, and today is my big pleasure to welcome Gian-Marco Rignanese from the University of Louvain in Belgium. So for those of you who don't know Gian-Marco, Gian-Marco is really leading scientist in electronic structure theory, and I think in the last few years took a lot of interest in combining electronic structure theory with data, to a point that in fact is intercalating this seminar in between a workshop that is organizing on data, essentially data for material science, so to speak. So, so it's great to have him here, and I think without any further ado, I'll just give the stage to Gian-Marco, please.
Thank you a lot, Stefano. So thank you very much for the invitation, and so it's a pleasure to present here today the work that you've been doing in screening materials from high-throughput ab initio calculation and combining that with data mining. So as you know, materials advances are one of the key drivers of innovation. We want to have faster computer, more compact energy storage, more compact data storage, and more efficient solar cells, just to name a few. But then how can we find material that have the targeted properties in this information age? If I were to ask around to, say, maybe friends or students of smaller school, they would say, okay, I would go on Google and I would try to say, if I'm looking for a battery material, I would just would like to type good battery material and hoping to find something like that. It doesn't actually work like that. If I were to ask my students, how do I get such a material? They would say, well, you have to search for a material that has a voltage comprised between 3 volt and 4.5 volt, that has good stability and good mobility. But still, that doesn't exist. And why is it that it doesn't exist? Is that because, unfortunately, we have very little information about the material's properties. So typically, if you consider the inorganic materials, which is about 50,000 to 70,000 materials that are known today, and we look at the fidelity constants, there's only 300 to 400 compounds for which fidelity constants are known. If we look at the elastic constant, there's only 200 compounds. The band gap's about 200 compounds. And so if we look at the complete encyclopedia of properties of materials, that is basically for each property a coverage of 1%. So if I've been able to come to Dublin on the campus and trying to find the seminar room where I would have been supposed to give the seminar here, look at the information that I would have had to find the room, basically it would have been impossible. In fact, we material scientists, when we design materials, operate basically in the dark. And if we take the example of Edison, who devised the bulb lamp, when he chose the material to put in the filament, he tested basically 3,000 material. And essentially by trial and error. They took one, tested it, it worked, it didn't work. And in the end, the material that he picked was not the best one. So luckily, thanks to the efforts that have been done in our community of ab initio calculation, the prediction of material has become so good, I would say, that we've reached a maturity that it's possible to screen materials by computing their properties in advance. So the way it works is as follows, typically. So we're going to take 1,000 to 100,000 of material, and we're going to compute different properties of this material, trying to see if the materials meets the criteria. So typically, we will have a given property number 1 here. So if the material has the good property, it passes to the second level, and we compute the second property, and so on and so forth, until it meets all the criteria in terms of the property that we want. As you can see, many of the materials end up in the trash. And some of the materials, typically 10 to 1,000, 100 of them, are okay. And if we have done a good work in the prediction, basically our colleagues can synthesize it, and I will show you an example where we did that. And so basically they have a material that meets all the criteria, and we have reduced the time that it takes to create the material that we want.
Sorry, Gian-Marco.
So yes.
So there are some comment that the audio is not great. Do you have a microphone close to you?
It's a microphone of my task. I don't think I can do something. Let's see, what can I do here? Maybe I should stop maybe the sharing of my screen because otherwise I don't have anything else. Yeah, maybe here, let's see.
Because it sound a little bit, it's not too bad actually, but it's not so super sharp, also on my side.
Okay, is this better?
No, actually this
No,
there is more noise.
It's worse?
Yeah.
Okay.
Now it's better actually.
Sorry?
Say something.
Now, if I speak like this, is it better or not?
Yeah, it sounds good now, I think.
Okay. So,
Sorry
okay,
for
I was saying that, is that okay?
Yeah.
Okay. So I was saying that the part in which we handle all those materials and we compute their property with so many materials, that's the realm of high throughput. And so there's been a lot of effort in this framework to allow for calculation of very different properties using an high throughput automatic approach. And I won't speak about that today. Now, the second thing is that everything that's in the dumpster here is not lost because we can create databases with the materials that for which we've computed the properties, and that can then be used to do machine learning, as I will show later on. So first, I'd like to show you an example of what can be done with this high-throughput approach before moving to machine learning. And the example that I'm giving you is the search for transparent and conductive material. Such materials are important to obtain, for instance, a touch screen where you want to touch the screen in such a way that the screen reacts, but you still want to see what's on the screen, so it needs to be transparent. And when you touch it, there is a current that flows on the screen, so the material needs to be transparent and conducting. The same is true for the upper layer of solar cells, in which you want the layer to let the sun go through, the light go through, to create an electron hole pair. And so it needs to be transparent. And once the electron hole pair is created, you want to separate the electrons and the hole. And so you want the upper layer to be conducting. But adding such materials that are both transparent and conducting, these are two antagonistic properties. And so it's not straightforward to obtain materials like that in a single materials where you have that. So a typical high throughput workflow, so the funnel that I was showing you before, would be something like this, where you search for material, of course, that are stable. They need to be transparent. As I said, they need to be conducting. And just to go through different requirements, for the transparency, typically we're going to be looking for a material that has a wide band gap in such a way that it's transparent. And for the conduction, we would like to have a material that has good conductivity. So it requires to have a low effective mass because the mobility of the carriers is related to the inverse of the effective mass. And typically, if we look at oxides, we have a situation, and that explains why it's difficult. In many materials, the top of the valence band has an oxygen p character, and as a result, you have a rather flat band for which it's difficult to have a low effective mass and it's a good mobility. So then for the conductivity still, you want to have a given density of carriers, and so you need to dope the material because otherwise the material is insulating since it has a big band gap. And so you can either dope it Ntype or Ptype and have density of electrons or density of the hole. One of the problems that is faced in finding a good transparent conductive material is that most of the existing materials for the moment are Ntype. And the reason for that is that they have these good mobilities that is basically 10 times larger than when you have a P-type, precisely because I was showing to you the fact that often in oxides, you have this OP character at the top of the valence band. And this difference between the P-type and that type is very limiting in terms of technologies, especially if we want to do transparent electronics where we want to have a CMOS, so a complementary MOS where there is both an N-type and a P-type thing. So that's a problem, and so it's interesting to look in that direction. And one of the questions that we try to address is, are there known oxides with lower hole effective mass that searching a needle in a haystack, or maybe by doing calculation, can we find the needle in the haystack in a limited amount of time? So I'm not going to go into the detail, but basically we screened the binary, ternary, and quaternary existing oxides, 7,000 of those. And we came up with one a double perovskite that was identified as an interesting one because it had a low effective mass, it had high valence band maximum with Ptype corrected, but it had a good band gap. And so we convinced some experimentalists to synthesize it. So they managed to synthesize and to dope it with potassium in such a way that when we look at the material, it is transparent, as you can see here on the left-hand side. And then it has a mobility which is basically 3 times larger than the typically existing materials that I use. So, well, all that was published, and I just mentioned here a review that we recently published in NPG Computational Materials. So, as I said in the beginning, we, based on these different studies that have been made in screening materials based on high-throughput, there's been many different databases that have become available online. Some of you know probably of AFlow in the group of Stefano. But there is other databases like OQMD, Materials Cloud, Nomad, the Materials Project. I'm more connected, I would say, to the Materials Project. And there's also some experimental databases. Maybe you know the COD, which is a crystallographic database where you can find many different structures. Most of these databases can be queried online through an API. And one of the problems is that the API that you have to use for each of these databases is different. And so typically, if you want to query for SiO2 in COD, the Materials Project, or AFlow, the query that you have to write, so typically that's a URL, this URL is completely different from one database to another. And so if you want to interrogate all those databases to do some machine learning, that's a nightmare for you because you have to learn all of that. And not only the query is different, but the answer, the response of the database is very different also. And so for those reasons, many of the developers of those databases gathered in different workshops. We started in 2016 in the Lawrence Center in the Netherlands, and then we had 2 conferences at the SECAM in June 2018 and 2019. We were supposed to have one in this week, and which we converted into a virtual event. And we are about to release the first the version 1.0 of this API that will be the same for all databases. So that will allow people to query all these databases and get a lot of data. So that's very interesting in terms of machine learning. And one of the things that you have to note, however, is that the computing time that is required to compute different properties is very different. So for instance, to compute the structure, chemistry, electronic properties, that's rather simple with DFT. Once you move to elasticity, piezoelectricity, phonons, it becomes much more complicated. It takes much more time. And so not surprisingly, when you look at the distribution of available properties within the databases that I just pointed before, you see that most of the data that are available are related to those properties that don't require too much time to be computed. And when you move to more advanced properties, there is still very few materials for which it is available. So one of the things that I would like to show you now is how we can go beyond that. For instance, if we want to predict the phase stability of different polymorphs at different temperatures, for the moment, most of those databases can provide you something like that at 0 temperature. For instance, in the case of the copper oxide system, you can get those convex shapes where you can find what is the most stable phase for a given composition. But if you want to go at a temperature that is different from 0, you should take into account the vibrational entropy. And that's more demanding because in practice, you need to compute the phonons, and this can be done with DFPT. So recently, we have generated an automatic workflow for computing the phonon thanks to Abinit, which is the code that I'm mostly working with. And so typically, we have something that checks how to parallelize the code automatically, how to do the self-consistent calculation, then treat all the perturbations that need to be treated, finally merges everything, analyzes the data, and then inserts them in the database. In this case, that's the Materials Project, where you can then go there, see the material, click on the the interactive plots, and you can even see how the atom moves for a given phonon, band, and Q points. And then finally, we do some tuning. Based on that, we have released the properties calculated for 1,500 semiconductors. So we have the phonon band structure, the LOTS splitting, the DOS, the Born effective charges, and also all the derived thermodynamical quantities. All this is freely available, so it's in scientific data. But as you see, the point that I would like to insist on, it's only for 1,521 semiconductors. It's more than the number that I showed at the beginning, but still that's very small compared to the 60,000 or 70,000 materials available. And so this is where machine learning might become very handy. So not knowing what was your level with respect to machine learning, I've put a few slides about explaining what it is actually. So what we would like to do is that we have an input collection of n data points. Usually that's referred to as the training set. And each data point consists of a series of attributes, the so-called features. And then there is a variable y, which is assumed to depend on those attributes. So what we'd like to add is that machine learning creates a model that gives you y as a function of x1 up to xn. And so that if you have new data, then you can make prediction of the y based on the x1, xn, which are known for that material. So usually a test set is set aside in such a way that you can test the accuracy of your model. So that indeed, once you have a data set of points, you split them into a training and a test set in such a way that you have a model that is validated. One of the things that need to be done is to reduce the dimensionality of the points. So when you have a given material, it can be characterized by very many different features. But what is important is to preserve the most important one, the main one. So typically here, if you look at the figure that you have here, you see that there is also an effect that reducing the dimensionality reduces the noise. So this step of going from a very precise picture with many features to something which is a bit rougher, that's referred as the feature extraction. So in terms of atomic structure, this is really a crucial point. We're trying to transform a given structure into a set of numbers, which can be put into a vector, which are describing the structure. Typically, the methods that I will be using are based on, there's many different methods. Those that I will be using here are one which is called ML4Science. Both of them are open source, and so you have the links here where you can go and check for these two. And the second one is called Magnet. I will come back to that. So ML4Science, what it does is that it gives you a bunch of features which are either based on the composition of the system that you're dealing with. It can be the element fraction, the mean atomic masses, the mean atomic row, and so on and so forth. And then you can also have features about the structure, which can be the space group, the crystal system, the radial distribution. And finally, you can have local features related to the local environment, the motif, so be it if the atom is in a tetrahedron, an octahedron, and so on. Magnet, in contrast, is a so-called graph convolutional network, and it allows a representation of the attributes of the atom. So typically you describe the atoms and its bond into a graph, and then there's some effect of convolution that is done in such a way that in the end you end up with some kind of vector which contains, in this case, 96 numbers which represent the structure. And so this magnet was developed by training the network, because it's a neural network there that converts the structure into these 96 numbers. That was trained originally on the formation energy based on the data that are on the materials project. So typically, as I was saying in the beginning, about 70,000 materials here. And the error was quite small, 28 MeV per atom. And there was trained also on the gap, and the error was 0.33 eV in that case on a smaller set of material. What was nice about this magnet is that when you try to look at the correlation between the elemental embeddings, so these basically the 96 numbers that represent the structure, with each other by checking their Pearson correlation coefficients, you can see that you recover something that looks very much like the periodic table. So if you look at the atoms, the way they are put one after the other, then you see that there is a lot of resemblance with the periodic table. So you see that in a sense, the machine learned by itself what's in the periodic table. Now, having a good model requires to train, to evaluate, and finally test your model. So typically, in the end, first you develop the model, and you need to test it. So you need to make sure that you extracted the most important feature, and you didn't leave some interesting one side. So it may be the case that sometimes you develop a model and you realize that it doesn't work, and so you have to go back to feature extraction to reach a good model in such a way that when in the end you have new data, you extract the good features from that data, and then your model works well, and so in such a way that you can make good predictions. So there's been different models that have been proposed. I'm just going to run through the ones that I'm using here. So typically one that I'm going to be using is the so-called random forest. And the random forest is made of decision trees. So a decision tree is how to classify a bunch of data based on a series of questions. So here I'm trying to classify fruits. So typically you can classify them based on the color. Is it green, yellow, red? And then according to the color that it has, I'm going to check whether I want to classify it based on the size, based on the shape, or again, based on the size if it's red. And then I can decide whether it's big, medium, small. In that case, I would have a watermelon, an apple, or grapes for the green fruits. For the yellow ones, depending on the shape, I would go for those that are round, and I would then distinguish those that are big from those that are small, the pineapples and the grapefruit and the lemon, and for the thin ones, I would have the banana. And then you see the example of the red fruit there. So this is a decision tree. When you put a bunch of decision trees together and kind of change the order in which you ask the question, this is why it's called the random forest, because you have many of those trees that are there, and they're created almost randomly, I would say. You can follow the path of the decision, and so here we say that when it's a yes, you would go on the yellow. When it's a no, it becomes gray. So if you follow the yellow dots, for instance, in the first one, you end up with a red prediction. In the second one, it's also a red prediction, but on this one, the one here in the middle at the bottom, you see that it's been predicted as green. So what the random forest does is that it looks at the one that is occurring the most, and it says, okay, my final prediction is going to be, in this case, going to be red, because it's 80% red and 20% green. The next kind of model that I'm going to be using is the so-called neural networks, where basically you have the different features that are combined together with different weights and using different so-called transfer functions, which you have there at the bottom. And these are then combined to create the output. So this is the simplest on the left-hand side. This is the simplest neural network that you could have. So basically combining all the entries with given points and then adding an output. But then what you could do is that, say, this output is not going to be my final output. So that's what's designed here on the right-hand side. You see that there is a first layer in which you combine the different inputs, and then those new ones are combined into other with different weights, and then you have many different layers in such a way that in the end you have the output. And the more you have layers, the more the neural network is deep, because there is many more layers. So the predictive power of a given model can be evaluated by the so-called cross-validation. Typically, you will take all the data that you have and split that into a training part and a validation part. So typically, the model is developed on the training part and then validated on the remaining part. And you see we can change, in this case, it's the so-called five-fold cross-validation, in the sense that you divide the complete amount of data that you have into 5 different sets, and you always leave one out and you train on the remaining ones. And then once you have done that 5 times, you average the error that you have made, and that's the global error that you create. The reason why we do that is that we want to avoid the so-called overfitting. Indeed, in any model, you can increase the complexity of the model to match the points better. If you don't have enough degrees of freedom in your model, you are in a so-called underfitting region. You see the example here where we have basically a curve, and we try to fit it with a simple line, and that's clearly underfitting. But if we go at the other end, where we have a polynomial of I level that basically is going to all the points, that's clearly overfitting. How do we detect that? Is that we see that the training error can always decrease when we increase the number of parameters in the model, but the data that have been set aside and not used to develop the model, the error that you make on those is going to increase at one stage, and that's the so-called validation error, okay, that increases. And so what you want to do is to be in the sweet spot here, where the validation error is the smallest, while the training errors is rather small. So I'd like to mention here the IntoMinor Effort, which is a tool that has been being developed in Lawrence Berkeley National Laboratory by Anubhav Jain and co-workers, where they basically have developed some tools in such a way that you enter the data, it auto-featurizes the different structures that you enter through MapMiner, then there's some cleaning, reduction, and then finally propose you a series of model, and that are supposed to be an interesting starting point for your predictions. When we look at the different models, the traditional machine learning models, such as the random forest, usually they are very easy to use, and with a limited amount of data, you can reach a decent predictive power. And when you increase the number of data, they have a hard time to improve. In contrast, the neural network and the more advanced graph neural network can increase their predictive power if you feed them with many more data. So the more data you provide, the better the accuracy, and you can see that the accuracy is better when you increase the number of layers in the neural network, and if you include those graph networks, you can reach a very good accuracy. The problem that we are facing as material scientists is that precisely the places where we would like to use the machine learning is the places where it takes a lot of time to do the computation, because otherwise our computation is already a good prediction of the properties of the materials, and we don't need the machine learning. So we need the machine learning precisely in the cases where it takes time to compute the properties. So if I come back to the example of my temperature-dependent energy, where I would like to include the entropy as a function of temperature, computing the phonons is very demanding, and I would like to be able to use the machine learning there. But unfortunately, that's precisely the point where I don't have many data. So that's why we went into this idea of trying to develop a new method to take as much as possible advantage of even a limited amount of data to extract as much as possible and to try to make reasonable predictions for that. So our idea is to have a feed-forward neural network, so that's a normal neural network, I would say, but we feed it with an optimal set of descriptors. So we do a preliminary effort in which the feature selection is done in advance, and we give a limited number of features to the neural network in such a way that it doesn't end up in a local minimum that is not very good in terms of prediction. And so the idea of the feature selection is to have an algorithm that takes into account both the relevance of the parameters and also avoids the redundancy. I will come back to that into details. So the idea is to put some prior physical knowledge and constraints into the choice of the feature in such a way that they are physically meaningful. And so in other words, this reduces the optimization space without needing to have many data to fix the weights that you have in the neural network. The bonus of our method is that we have developed an architecture that allows to learn on different properties at the same time, and I will come back to that as well. So for a feature to be relevant, you want to have some interrelation between the feature and the target. So in the two examples that you have here on the left-hand side with these red points, you see that the feature 1 and the target are not very much interrelated. In contrast, clearly feature 2 is very well related to the target. So that's typically a feature that you would like to keep and to enter into your neural network. One way to measure how the target and the features are interrelated is the so-called Pearson's correlation coefficient, which measures this interrelation. So for instance, you see here a bunch of graphs where you have a perfect positive correlation at the top upper left here, okay? And at the bottom, you have a perfect negative correlation. In between them, you have no correlation. And then you have different degrees, either of positive or negative correlation, all of them being measured through this R coefficient, which is 1 in this case, goes to 0.9, 0.5, 0, and then adds up to -1. So it's very interesting to find the correlation between a feature. And so typically if you have features that have a strong correlation with the target, that's a feature that you would like to take. The problem with the Pearson coefficient is that it has a series of limitations. One of these is that you see here again an example where there is no correlation. The R is equal to 0, but then this correlation coefficient is also 0 in this case where you have a parabola. So if you had a feature that is clearly related to the target as being y is equal to x squared, you would have a correlation that is 0, which is annoying because you would throw it away. So we decided to use a different feature selection. It is based on the so-called mutual information. Typically, the mutual information between two random variables is a measure of how they depend on one another based on the so-called entropy. So typically, if you have two variables, x and y, you see that you have two ensembles there, the red one and the blue one. The mutual information is the part that is that you know for both of them. So that's the one that you know from one and the other. You have the part that, so the one that is called hx minus y, which is what you don't know about x when you know y. And reciprocally, hy minus x is what you know about y when you don't know x. So what you want to have is to have features that have a lot of mutual information with the target. And what we use here is the so-called normalized mutual information, which is typically this mutual information divided by the entropy of x and the entropy of y. In such a way that when you have two systems that have basically no interrelation between one another, this normalized mutual information is 0, whereas it is 1 when it's a perfect matching between the two. So typically, we will choose the first feature in the dataset by choosing the one which has the highest normalized mutual information with the target variable. And this will help us also to gain some information about the physics. Because indeed, by choosing this feature and then the next feature, we'll see that it will tell us what are the most meaningful features in terms of the physics. I'm going to show you here the example of the vibrational entropy that was mentioning there. So we have tested, based on our calculation of the phonons, we had the vibrational entropy on this roughly 1,500 materials, and we tested this algorithm, and we saw that the first feature that has the biggest normalized mutual information with the entropy is something which is related to the interatomic bond length, which is not very surprising. If you have a big bond length, then probably there's not a big force constant between the materials. And the second one that comes out is the valence range of the constituent elements. So that's basically what is the difference between the largest valence, the smallest valence, and that's in some way a measure of the ionicity of the bond. And so here with two simple features, you see that when you plot the vibrational entropy as a function of the first feature, and then you color as a function of the second feature, you see that there is a clear trend as a function of the first feature, but there's also a clear trend as a function of the second one, the purple ones being at the bottom and the yellow ones being at the top. So we have the choice of the following feature are made on the idea that we want to avoid redundancy, because two features can have a strong relation, interrelation with the target, but if they are strongly interrelated one to another, you're not bringing new information to the neural network. And so what we do is that we define a relevance and a redundancy score, R, which is defined as follows. So if we have a subset of selected features, so I told you how to select the first one. Once you already have one, the next one will be selected in such a way that it still has a big redundance, a big, interrelation with the target feature, but you want not to have too much redundance with respect to the previous features. And so you see that there are two parameters here. There's this P and the C. If the part with the P was not there, so if the brackets were not there, typically we just have as a criteria the relevance of the feature. And in contrast, if you have a big P and a small c, what it matters above all will be the avoiding redundance. And so we have to play with that. And especially the more you have feature, the more the redundance is, sorry, it's the contrary. The less you have feature, the more the redundance is important. So really the first feature that you want to put as interesting feature are those that are bringing new information in the neural network. And so the procedure continues up to the moment where you reach a certain number of features that you consider to be sufficient. It can be fixed arbitrarily or optimized in order to minimize the error of the model. So this is the part in which you select the features of the model. So as I said, this model is based on this feature selection. That's this modnet that we are presenting. We start from MapMiner. From a given structure, we generate very many different features. We do this feature selection, and then we feed them to a neural network. And then the next thing is to take advantage of the fact that we have many different properties. So typically in our case, we had the vibrational entropy at different temperature. We had the free Helmholtz energy at different temperature. We had maybe the formation energy. And so what we do is that there is a part that is common to all these features. That's the green box that you have here, which is going to be common to the different features, but then to the different, properties of the materials. Oops, I'm sorry, I went too fast. And then when you have parts that are groups of properties that are common, so for instance, all the dynamical properties, whereas here you would have the formation energies, and then at the bottom here you have, for instance, the different temperatures. So my property A depends on different temperature, pressure, different things. And all the data that you have, you try to feed it in such a way that there is a common part that is learned jointly. And in the end, you have a unique machine learning model that predicts all the properties in one go. As a result of that, to come back to this problem that I was showing you before, what has been done before, indeed, because people didn't want to do the FPT, is that they trained a machine learning model. And this is work that was done by the group of Stefano Furtarolo and Natalia Mino, in which that's the blue cross that you have in this point and this plot here. So where they trained their model based on about 300 materials, and they obtained an entropy for a machine learning model for the entropy. And basically, the error that they're making is in line with what we have for a random forest that is based only on the composition, which is the C that you see there. CRF stands for a random forest that is based only on composition. And so here you see the effect of the size of the training set. When you have a small size, the error is big. And when you increase the training size, you reduce the error. But for a random forest, at one stage, you cannot plateau. If you include information about the structure, this is this random forest here, that basically takes all the features from the MapMiner. So it takes all of them, basically, and then does this random forest thing. You see that you have improved compared to what was done before. And the random forest here, in a sense, is doing an automatic selection of the most important features. So for the random forest. Then we tested the magnet that I was telling you before, so that uses convolutional graph networks. And that one is really something that requires a lot of data. You see that it's doing a better job. It's a neural network. It's doing a better job than the random forest, even for small dataset size. But we have come with this idea, and we have further improved compared to what was existing. So here you may say that it's a small effect. It's not very big indeed, but still, if you look at a zoom of these data, you can see that the improvement is noticeable. And compared to a neural network in which there would not have been any feature selection, so that's the orange curve that you have here, you see that when there is no feature selection, especially when you have a small training set size, the difference is noticeable. So it's really important to do feature selection prior to feeding your neural network when you try to develop a machine learning model. Finally, when we learn on all the properties simultaneously, that's an improvement compared to the other models. It's very small compared to our ModNet, but the advantage is that we have a single machine learning model that gives us all the properties at the same time. And as a result of that, what we can obtain is that we can obtain curves. So here I'm comparing the different thermodynamical properties, entropy, enthalpy, specific heat, and internal energy, the DFPT computed one, which are solid lines, and then the machine learned ones, which are the dashed lines. In most of the cases, we have very good results, and you see 3 of those, which are almost on top of one another. But just to be fair, I wanted to mention that we have some cases in which we still have some error, and we're going to try to improve that if possible, maybe by improving our methods or by adding more data. Nice thing is, once we have that, we're going to be able to produce those comparison of different polymorphs of a given species, given compounds, and as a function of temperature. And so we'll be able to say which phase is more stable at a given temperature. Of course, we will have to pay attention in the region where the differences between 2 systems is small, to the accuracy that we have based on our machine learning model. As a final example of what we have done, I would like to show you some work that we have done on the optoelectronic properties. So we're looking for materials that have both a high refractive index and a high band gap. So we want a high refractive index because it improves the performance of the optoelectronic devices, and it increases the response in the nonlinear regime. We want to have a high band gap because it allows to guarantee transparency over the visible spectrum, and it also allows to work at higher temperature and to switch with larger voltages. The problem, a bit like in the case of the transparent conductive materials, is that these 2 properties are kind of contradicting in the sense that there's an inverse linear relationship between the refractive index and the gap. So when the gap increases, the refractive index decreases. And this is confirmed by DFPT calculation. So we did 4,000 DFPT calculation on a broad range of chemistry, and we obtained this data points. So there had been previous work to try to obtain models for that. I'm not going to go into all the details, but I'm just going to show them to you. I don't know why it's a bit slow, but okay, here are the results. And typically, all these models are not very satisfactory. And to be fair with the guys that developed this model, the reason for that is essentially that they didn't have many data to fit their models. Typically, they would have 60 to 100 data to fit their models. So what we did first was to work on the physics, and we understood what was happening from a physical point of view, and we obtained a description of all the data based on single parameters that allowed us to interpret the data. But still, I mean, to do 4,000 computation, it took some time to do that. It's not impossible, it's really doable, and we did that actually. But if you want to do it for 60,000 materials, that's a bit more complicated, and this is why we turn to machine learning. So the red point that you see here are the data that you've seen in the previous slides, the DFT computed ones, and the blue ones are those that have been evaluated by the machine learning model that we developed based on those data and using the structures from the materials project. structure that we are interested in are typically those that are the ones that have in the high part of the distribution, in the sense that you want to have a gap that is as large as possible, and a high refractive index. And so we selected some of the outliers there, and we computed the refractive index. So for those that have been predicted to be interesting for machine learning, and we compared that with DFT. And as you can see in the table here, you see that the predicted value, so that's the ML value there, compared to the DFT computed, which we did afterwards, after we predicted that, is very good. So there is an error, of course, but it's very reasonable. And clearly we can predict materials that are interesting. And so with this, I will conclude. I think that I've shown you that it is possible, based on high throughput ab initio computing and complementing that possibly with machine learning, to discover materials that have specific properties for a given application. And then I finish by thanking my collaborators on that. So the people that did the work in UCLouvain, Pierre-Paul Debreuil, Nicolas Garden, Francesco Naccarato, Guillaume Brunat, Guido Pacetto, Francesco Ucci, Gabriele Gautier, Matteo Giacomassi, and then my colleagues and Professor Xavier Gomez and Jean-Paul Thier, and then people in Lawrence, Berkeley, Alex Dunn, Patrick Wick, Matthew Norton, Sham Dwarakat, Anubhav Jain, Gerd Cedar, Christian Person, and in Santa Barbara, the group of Shruti Ong and the student Chicha. And I thank you very much for your attention.
Thanks a lot, Gian-Marco. So I'll clap, as there is nobody in the room with me. So.
Thank you for the clap.
Thanks a lot. Actually, there are quite a few questions already that I can see on the chat. So I'll maybe just go through the questions. Okay, the first one is from Rajarshi Tiwari. He's a postdoc in my own group, and essentially he's asking if you can go back for a second to the mutual information part.
Yes. So the part is where I define it, or
yes. So yeah, right. So essentially, it was asking whether you can explain again this pie chart. So I guess the concept of the mutual information.
So typically, okay, it's a way to measure the amount of information that is common between two variables. So in one variable, when you observe the other one, so what's the probability that X has a given value if you know that Y has another given value? It may well be that you have no information from on X if you know something about Y. In that case, you would have basically no mutual information. In contrast, it may well be that if you know what's the value of Y, you directly know the value of X. In that case, you would have a perfect mutual information. Typically, if you have a variable Y, which is X squared, and if you know X, you clearly know Y. In that case, you have a mutual. So it's a better way to measure the correlation. As I said, the main reason for introducing that is that in the case of the Pearson correlation coefficient, when you have typically this Y is equal to X squared, the Pearson coefficient is strictly zero, really zero. So that means that you seem to have no correlation. Whereas clearly, when you know the X, you know the Y in such a case.
And maybe, Gian-Marco, sorry, no, good. Yeah. No, I mean, I might have a very quick follow-up question on this. I mean, so essentially you use this criterion to correlate with your target variable, right?
Yes.
And essentially then you go in order. So you take first the most correlated feature, and then the second one, and so on. I mean, I guess the total number of features you add in eventually might depend on the accuracy you want to determine your feature, right?
Yeah, that's what I've written there. So so we put a number of features, and so the way we decide the number is either you say, okay, I want 1,000 features, which is fixed randomly, but indeed, I mean, you can try to minimize the error that you do. And you can see that at one stage you are adding feature, and that's not improving the error. So you don't want to do that. You're wasting CPU time or GPU time, to be more precise, to optimize your machine learning model. So indeed, that's something that you can tune.
Okay. Then I have another question from Maxim Markov. I'm afraid I don't know.
I know him. He's in my group.
Oh, okay. So that's easy enough. Okay. And so that's interesting. Okay. So the question is, have you tried to validate the prediction of your model on other databases, such as the one of Togo?
For the vibrational entropy, not yet, not yet.
Yeah, I think
But
it was
I mean, in that case, so okay. First, we have on the database of Togo, we think that the density of 2 points that they have might be not sufficient, and so we don't know whether the thermodynamical properties that they have. I mean, in that case, you are introducing an error also on the data. I mean, here we're trying to reproduce our data, and so it's not a validation in that case because you have an uncertainty on the property that's there. So it's two different things.
Okay, then I have a question from Sabine Korbel, was in my group, and she's asking, how do you arrive at the numbers of known band gaps and electric constants?
Say it again.
I mean, how do you arrive at the numbers of known band gaps and electric constants? So I guess it's a question of where the data come from. Yeah.
Oh, it's just by I think it's numbers that I found in an easy way to check the literature. I would say, just I guess that it refers to the number that I was showing at the beginning here, if I understand correctly the question, which is this one here. Let me just show the slide. I guess that refers to these numbers here, the band gaps and elastic constant, I guess, not lattice constant, because I didn't speak about the lattice constant.
Possibly, yes.
Okay, so I mean that's if you typically go into Landolt and Bornstein, that's typically the kind of numbers that you would have. You would have the lattice constant, the elastic constant for about 200 materials. These are just numbers, and they will be that it's a bit larger than that.
And actually, so there's another question from Maxime, and he's asking, don't you think that predicting the coefficient in the energy expansion rather than predicting the thermodynamic property is a more natural machine learning approach for vibrational properties?
So predicting the properties in terms of the energy.
So yes, so don't you think that predicting the coefficient in the energy expansion rather than predicting the thermodynamic property directly? So I guess the question is, can you go for the energy first instead of going directly for the thermodynamic quantity?
To go for what first? For the DOS? I would say that it's the DOS, I guess.
No, I guess the total energy, right? To predict, the DOS, yeah, the phonon DOS, for instance, yeah, right, yeah.
It's a different way to do things. It might be interesting to check the DOS, but then you come into the problem, how do you describe the DOS and predict the DOS? So you have to bin the DOS, and then you add more information about, or more variables about, and indeed, I mean, once you've predicted the DOS, you have all the properties. So it's a different way to do things. I'm not convinced that it's better to get the DOS rather than the properties.
Yeah, I mean, I guess he has a follow-up comment and essentially said, look, if you predict the DOS, you also have the DOS. So if the DOS is an information that you need, is there as well, I guess.
Yeah. But I mean, usually in terms of predicting materials with a given properties, you don't care about the DOS. Usually you have a target property that you would like to know. And in this case, that's the stability as a function of temperature. So right. The DOS per se is not really interesting.
Okay, so let's see if more questions are coming. I have actually a quick question myself. Now, so you discuss essentially how you get the most out of a database which don't contain too much data, right? And I guess a very good example is experimental databases, right? That these are bloody difficult to. So I just wondered actually, what is your kind of idea about? I mean, what is the prospect to have a real integration of experimental database in all this pipeline? Because I mean, we calculate a lot of stuff, right? But then it's much more tricky to get experimental information.
Yeah. So I've seen recently an article, and I actually discussed with him from the Shui-Ping that I was mentioning at the end there. It's on the archive, where they use something which they call multi-fidelity. Let me just put his name again. So that's Shui-Ping here from Santa Barbara. So they use the so-called multi-fidelity. So the idea that they have there is that, for instance, for the band gap, saying that you have a limited number of data sets from experiments, but you have many results from DFT, 60,000 maybe. And so you try to learn both simultaneously. And so you have a machine learning model that takes both into account. And that they show that it improves the results that you have on the experimental gap compared to just using the experimental gaps. I don't know if that was clear. So you take advantage that you know some other stuff from the materials, be it computed or even be it measured. That was one of our idea. So if we, the model that I showed here, the multi-property that I showed, if you have experimental curves for different temperature, different properties, you can combine all that. And we hope that by learning all that together, you remember the green part that was there, can be better because it learns from different bits of the material. If you want.
I mean, I guess.
I think.
No, sorry.
Yeah, I think that's my prospect is that trying to learn precisely either for a bigger set of materials and then use that information for that's some kind of transfer learning, possibly joint learning. That's the way I see where improvements can be done.
I mean, I guess
the other way.
Yeah, I mean, I guess the difficult bit is that theory is essentially very well under control. So in a sense that okay, you have your unit cell, you know exactly what you're calculating. Experiment, you grow a sample, and I mean, two identical sample might have different property because actually they're not identical. In fact,
Indeed. I mean, we've been discussing yesterday and today in Optimate because we want to extend. So for the moment, Optimate is essentially based on the structures, and we would like to extend that to properties. But then we had a lot of discussion with Nicola Mazzari, and because it's it's the property of what. I mean, from our point, in theory, it's easy because we know what we have computed. But then in experiment, there's something, maybe there's the composition, but even sometimes the composition, there is some uncertainty on the composition.
Right.
So yeah, we know that we have to live with that. So that there is, I mean, that's also one of the reasons that I was mentioning to the first question of Maxime compared to Togo. I mean, there we're running into two different sets. It's like if I was sitting on two different experimental data sets, which have been measured by two different groups with different errors on their data. And that's very complicated to handle also in terms of confidence and so on. Unfortunately, I think that we have to live with that.
Actually, so there's another question from Sabine, and it is about the very last, one of the very last slides you show when you have the DFT perturbation theory result and the machine learning. And essentially, she was noticed that it looks like that they're all around a specific, I mean, all around a value of 2, right? And I just wonder whether, essentially, she's asking, would you have a larger error? Right. So I think.
No. This is just. I mean, we've done tests. Okay, I couldn't show all the tests we've done, but all the tests that we have done are very, very reasonable. I mean, typically we have errors that I would say 0.2, 0.3 on the refractive index on average. So, which is actually, to be precise, the mean average error is smaller than 0.1 on the refractive index.
Right.
Whatever on the complete data set.
Okay.
This is just on the this is focusing on those that are interesting in terms of being interesting, meaning they are for a given gap, they are among those that have the biggest refractive index. So typically here, the reason why it's 2 is because I was focusing in this region here of interest.
Okay, so I don't see any more questions. So if this is the case, I just would like to thank Gian-Marco again and all of you out there
for the invitation,
for listening. And I guess we are going to have a new seminar next week. Thanks, everybody. Cheers.
Thank you all. Bye.